Hello everyone, I am Eren Güler. I am senior year student in the Hacettepe University Electrical and Electronics Engineering.
And hello, I am Aliberk. I am Hacettepe Electrical Electronics Senior Year student. This is our graduation project Space Object Classification, and our supervisor is Professor Dr. Seniha Esen Yüksel. Space situational awareness refers to the ability to track, understand, and predict the behavior of objects in space, particularly in low Earth orbit. A space object refers to any physical entity that exists in outer space. Some of them are satellites, rocket bodies, debris, and sometimes they are meteors that entering our low Earth orbit. Classification of different objects is critical to ensure safety, sustainability, and effectiveness of space operations. So, what is a light curve? As you see in the right figure, we have multiple light curves of multiple space objects. A light curve is a graphical representation of how these brightnesses of a space object changes over time. The aim of the study is to analyze the temporal variations of light reflected by objects in orbit, known as light curves, to gain insights into their behavior and characteristics. By leveraging these light curves, the study seeks to develop and implement innovative algorithms for classification and characterization of space objects. Here we have our methodology scheme. For the first three parts that will create our light curves as our data to feed our neural networks, we are using a software package called STVIT. This step processes input images by removing noise, adjusting contrast, and filtering to enhance visual object visibility to ensure consistent data. So here you can see a detection made by the STVIT software package. They use 3D hue transform. This is the final step of the STVIT scheme. LC generating is very important for us since we will be using light curve data to classify and characterize our space objects.
Before feeding these light curves to our deep learning model, we apply some preparators. First, we apply a discrete wavelet transform to reduce dimensionality. Then, we are padding these light curves to get a fixed size for our deep learning model. At last, we apply a normalization part to reduce the computation time. In this slide, you are seeing three different light curves belonging to three different classes named satellite, rocket body, and debris. We tested three different deep learning models for the classification part. First, here is a rocket model. Rocket is a state-of-the-art deep learning model used in time series classification tasks. It is based on random convolutional kernels. Because our dataset is complex, as seen at the TSNE graph at the left top on the screen, we did not get very good result. After the rocket model, we created a new architecture based on the convolutional LSTM layers, consisting a total of 17 layers. The architecture can be seen in the slide. To further improve the convolutional LSTM model, added a transformer part to the previous approach. The architecture can be seen at the left side of the screen. Here you can see the results for the convolutional LSTM model. From the confusion matrix, we can see model is performing well on rocket body and satellite classes, and it gets a total accuracy of 80%. Here are the results for the hybrid convolutional LSTM and transformer model. We can see from the confusion matrix this model performs worse from the previous approach, and it gets a total accuracy of 74%. Here we can see the overall results for all three models we tested. We can see the convolutional LSTM model performs best on overall between these three approaches.